Hi, my name's Wyatt Eames. Tonight I'm going to be explaining a little bit about homeostasis, about how things cross across the cell membrane, and about the process of osmosis. So I'm just going to be using this little notepad here. And first I wanted to talk about homeostasis. So let me write that out here at the top. Homeostasis. Homeostasis is the process of maintaining a stable internal environment in the body despite changes to the external or also the internal environments. One great example I like to use is of the internal temperature of the body. So I'm just going to draw this little graph here. And let's say this side is temperature. So temp, the body temperature usually is going to be ranging around about 96 to 100 degrees in a healthy individual, and then kind of got like that sweet spot at 98 degrees. And then if we measure the body's temperature over time, so let's say 2, 4, 6, 8, 10 in hours, what we see, so let's say we kind of put these dots anywhere, what we see is that all of these temperatures are usually going to stay within um, this little range here, and what we call this is the normal range. So normal range. And what the normal range is it's an area that is trying to stay as close as it can to something called the set point. Set point. So the set point is kind of like the average or the best temperature or whatever that the body can be at, the most healthy point that it should be at. And obviously it's going to fluctuate around that, but the temperature, as we see, is kind of always going back towards the set point, and it's always going to be changing because of varying factors. It always wants to get back to that set point, and one of the ways that it does that is through things that are called reflex control pathways, or in other words, we can also call them feedback loops. So, feedback loops. And what a feedback loop is it is the way that we're able to adjust to our environment or adjust different things inside of us to our environment. Um, a feedback loop or a reflex control pathway begins with a stimulus. That stimulus is going to be caught by a receptor. Sorry. Receptor. What the receptor is going to do is it's going to send a signal to a control center. Most control centers are going to be in the brain, but there are other ones. And then that control center is going to decide what to do with the information it's received. And then once it has decided, it'll send another signal to an effector. And the way that the receptor, let me just do this, the way that the receptor is able to send a signal to the control center and then the control center to the effector is going to be through something called an afferent pathway if it's going towards the control center, but if it's going away from the control center, it would be called an efferent pathway. And these are both usually through neurons or blood. So put that up down here. blood. And basically these reflex control pathways, these feedback loops, the end goal is to get us back to this set point right here. So we want to get back, if it's the case of temperature, let's say the stimulus here is going to be a decrease in temperature. You go outside into cold weather, your receptors or your skin is going to sense that. It's going to sense a decrease in temperature. It's going to send a signal to your control center. The brain is going to receive that and then send a signal to the effector, which would be your muscles to make you shiver, or your blood vessels to kind of get smaller, to contract, so that we can conserve some heat. And what that is going to end up doing is increasing our body temperature. So that is actually going to make it so that our receptor here does not feel this stimulus anymore. So the receptor is going to feel that our body temperature is coming back to normal. It'll stop sending the those signals to the control center, and we will be good. We'll return to our set point or our normal range of temperatures. What I just described is something called a negative feedback loop. So anytime an effector is going to help restore our body temperature or restore anything to homeostasis, that's a negative feedback loop. It basically, what a negative feedback loop does is it restores the body system to equilibrium when there are deviations from its set point. So there's plenty of examples of this, and basically they are all pretty similar to this temperature one. There's also something called a positive feedback loop. What happens with a positive feedback loop is it's kind of like a runaway cascade effect, and 95% of the time it's not going to be good. It's not something that we want to happen. There are a couple of cases, such as pregnancy, when we start contractions. That is a good positive feedback loop, but for the most part, this is not going to be good. And so what's going to happen, let me just use an example. For example, let's say we have an open wound. So we cut our leg, and there's blood coming out of the leg. We have an open wound. What's going to happen is that's going to create a stimulus, which what will happen here is blood pressure will decrease. So when that blood pressure decreases, it's going to cause our receptors in the blood to realize that the blood pressure is decreased. They're going to send a signal to our control center, and our control center is going to say, oh goodness, we need our blood pressure to get back to normal, so let's send a message to the heart, and the heart is going to be the effector here. It's going to start pumping faster. So it's going to start pumping faster. As the heart pumps faster, more blood is going to come to the wound and get spewed out. It's a little graphic. And as more blood spews out, the blood pressure is going to continue to decrease. So more decrease in blood pressure is the stimulus. More receptors are going to send messages to the control center, which are going to send more messages to the heart to pump even faster. And as that happens, eventually we have no blood left, and we die. So not good. The majority of the time, like I said, positive feedback loops are not going to be good. But basically, this arrow kind of shows it. So it goes from the effector to create more stimuli, which increase the amount of signals the receptors send, which increase the amount of things the effectors are doing, and it's kind of a cascading effect until we die. So most of the time we're going to want some medical intervention when there's a positive feedback loop to help us get back to homeostasis in that normal range of homeostatic area. That's kind of what homeostasis is going to look like. And then the next thing I wanted to talk about is the diffusion of different molecules into and out of the cell. So let me just do this diffusion. And when we think about this, there's a couple different types of diffusion that we talked about in our class. But I just want to draw this little tank out. Basically what happens with diffusion is when you have a different amount of solutes in one side compared to the other, if there's a semi-permeable membrane, these solutes are always going to want to come over here until it's balanced on both sides to create homeostasis, or to create an equal amount, sorry, not homeostasis, but to create a equilibrium on both sides. So it's the same thing with our cells, but not everything can just come in and out of our cells. The cell is made up of a phospholipid bilayer, and not everything can actually get through this bilayer. So we've got a bunch of little, kind of like that. Not everything can get through this bilayer, just using its kinetic energy, which is what causes these cells up here to move from one side to the other, or these molecules up here, sorry. So I wanted to draw out a little chart here that kind of illustrates this. So there's two types of transportation across a cell. One is if they are using kinetic energy, and one is if they're not. If they are using kinetic energy, this is passive transport. If they're not using kinetic energy, this is active transport. And for example, there are some molecules that are able to diffuse through the membrane. One of those, or some of those, are such as oxygen and carbon dioxide, and that is called simple diffusion. So we'll just say O2, CO2, and basically what happens here is they just freely pass through the cell's membrane. Easy, right? But that's not what we're here to talk about. What we're here to talk about is protein-mediated transport. So when we talk about protein-mediated transport, there's three different kinds, and these first two kinds are going to be through passive transport. The first kind is going to be called carrier-mediated transport. So what happens with carrier-mediated transport is, or sorry, let me just restart on this part. So the first kind is actually going to be called diffusion through channels. Sorry about that. When stuff diffuses through channels, let's draw a little cell membrane here. So there are going to be different particles, such as sodium ions or potassium ions, and they have different gradients inside and outside of the cell. So if there's a higher concentration of sodium outside the cell and a lower concentration of sodium inside the cell, sodium is going to want to come in. And vice versa, if there's a higher concentration of, say, potassium and a lower outside the cell of potassium, then potassium is going to want to leave the cell. Diffusion through channels takes advantage of that, but what it does is it has higher specificity than simple diffusion. Usually the channels are only allowing specific ions to pass through them due to a selectivity filter. Another thing that they do is these, let me just use the eraser here to clean this up a little bit. A lot of times these channels will have a gate on them, like so, keeping things out or keeping things in. These gates have three types. So I'll just put those down here, or no, let's put them over here. There's three types of gates. There's mechanical, which is usually triggered by pressure or other physical stimuli. Voltage, which is triggered by an increase in the charge outside or inside of the cell, which is what causes it to open. Usually when the inside of the cell becomes more positive, it'll open. And then there's also ligand gates, where ligands will have to come and bind to this door right here for it to be able to open. And then specific ions will be able to come in and out freely according to their gradients. To talk about the rate of the diffusion through the channels, it's relatively fast. The channels provide a direct pathway into the cell, so it's relatively fast. It takes no energy, it's all passive, so it requires nothing. It's just dependent on the gradients of the ions that it's transporting, and saturation only occurs if all of these channels that are on the entire cell are taken up. But because it's so fast, usually that's not going to happen, and they're always going down the concentration gradient, like I said. The next type I wanted to talk about, we'll take it down to this next page, is carrier-mediated diffusion. That's the one I said earlier. Carrier-mediated diffusion. And what this is, there's a protein, the same as before. I'm just going to kind of draw the cell membrane like this, but now there's a phospholipid bilayer there, and there is a protein right here in the cell membrane. And let's actually move this over a little bit so we have more room. So with carrier-mediated diffusion, carrier proteins are not like a tube in the example above here. They're not quite like a tube. They're more kind of like a revolving door. So if you imagine a revolving door from above, let's say these are the walls of a building, and you have your revolving door that's constantly spinning around. The person could enter right here and then exit right here, but at no point is the door ever going to open to the outside and the inside. It's always going to be partly closed, and that's kind of how these carrier-mediated diffusion proteins are going to work. So basically they're going to be pretty specific. They'll have a binding site for a certain ion or molecule, and what will happen is that molecule will come and bind on the protein, and then the protein will, once the thing is bound, once the molecule is bound to the protein will start to change shape and kind of envelop the molecule and then spit it out on the other side into the cell. And that is all according to the molecule's gradient. So if we have a higher concentration out here and a lower concentration out here, the molecule will go through this protein. This one's definitely going to be a little bit slower, the carrier-mediated protein, versus the diffusion through channels, just because of there's multiple steps in the process. But it is still passive, relying on concentration gradients. And saturation also is more likely to occur here just because of that slow timing. And if all of these gates are taken, then it's going to be harder. If all these gates are taken, then nothing else can get into the cell. And like I said, this is always going down the concentration gradient. Besides passive transport, there's also active transport, which I'm going to just take it down here and write again. Active transport. And there's two kinds of active transport that we're worried about here. The first one is called primary active transport. And what primary active transport does is it moves the solute against its concentration gradient using carrier proteins that are similar to the carrier proteins we discussed earlier. So they're kind of like this one in the carrier-mediated diffusion, but they're going to be moving them against the concentration gradient, and they're going to have a binding site as well for ATP. So I'm just going to draw this out. So what's going to happen is this, for example, there is one kind of protein that is called the Na, or the sodium potassium ATP ACE pump. And what this one does is once an ATP binds inside of the cell, and once a potassium, sorry, let me see. Comes and binds to the outside of the cell, and then a sodium binds to the inside of the cell. So what's going to happen is once there's ATP, potassium actually does not want to get in here. There's a higher concentration of potassium inside the cell than outside. And there's a higher concentration of sodium outside the cell than inside. So neither of these two want to go in or out of the cell. They want to stay where they are, but they bump into this protein, and what happens is it uses ATP, and with that energy, it's able to pump 3 sodium ions out of the cell and 2 potassium ions into the cell. So that kind of active transport, the primary active transport, is going to use an ATP to pump different solutes against their gradients. It is definitely a high specificity. It has a slower rate than diffusion due to the energy requiring step of ATP binding. It's dependent on that ATP, and it's going against the gradient, like I said. The other kind of active transport is going to be secondary active transport. And what secondary active transport does is we have another protein in the membrane of the cell. and say there's something outside the cell that wants to get in, such as sodium, and then there's something that we need to get out of the cell, such as glucose, but sodium wants to get in here. Glucose does not want to get out. Glucose wants to stay in. So what we're going to do to fix that, let me erase this, is this protein is going to bind sodium. Once sodium is binded, it's going, and glucose is always also binded. Sodium's gradient is going to cause it to come into the cell. When that happens, the energy is going to allow glucose to get taken out of the cell like that. So using the gradients, which were created by the NAK, or the sodium potassium ATP pump, we're able to export molecules, or whatever molecule in whatever direction against their gradient. So this is also high specificity. It's also slower than channel diffusion. And basically we're relying on ATP indirectly, but really we're relying on the gradients that were established by the ATP. And so one molecule is going to move against its gradient, one molecule is going to move with the gradient. And that is about it for the diffusion here. And last, I wanted to just quickly talk about osmosis. Osmosis is the passive movement of water across a semi-permeable membrane. So say we have this semi-permeable membrane, there's water, we have some sort of solute over here that cannot cross the membrane. What's going to happen is water, to balance out the concentrations, is going to leave the left side and join the right side so that the concentrations can be more similar. Usually it will go until equilibrium unless it is stopped by some external force. With osmosis, we have something called osmolarity, which is different than molarity, which I'll talk about in a second. Osmolarity is basically the number of particles, of solute particles per liter of solution. So if we say osmolarity, osmolarity versus molarity. Molarity is going to be the number of moles per liter solute, or solution. So moles of solute per liter of solution. Osmolarity is going to be the number of particles of solute per liter solution. So if we take two examples here, like glucose and salt. Glucose, if there's 1 mole of glucose in a solution, it'll be 1 molar glucose solution. Because glucose doesn't split into smaller particles when it's dissolved in water, it's also going to be 1 osmol equivalent in the liter of solution. So those two things would be the same. Molarity and osmolarity would be equal to each other. But with salt, with NaCl, what happens is when it's dissolved in water, they separate into 2 particles, Na plus and Cl minus. So now there's 2 particles instead of 1 in this solution. So it'll still be 1 molar if there's 1 mole of it per liter of solution, but it's going to be 2 osmolar. So that's kind of the difference between osmolarity and molarity. And the way that we can kind of compare the osmolarity between two solutions is I will show right here. So let's say we have a cell and we have an IV bag of solution. Inside this cell, the osmolarity is going to be 300 milliosmoles of particles. And say inside this bag we have a 0.9% saline solution. A 0.9% saline solution is measured to be 300 milliosmoles of solution. So if these two are the same, then they are going to be isoosmotic. Let me just isoosmotic. But if we change something about this and we decrease, let's say we put, for example, a 0.45% solution saline, then it's going to decrease to about 150 milliosmol. If the osmolarity of the cell is greater than, let me just draw that again, greater than that of the IV bag, then the IV bag compared to the cell is going to be hypoosmotic. If we increase the amount of saline and we do, let me just erase this, say like a 1.8%, then what's going to happen is it's going to increase to 600 milliosmoles, and it'll have a greater osmolarity than the cell will, so it's going to be considered hyperosmotic. So that is how we compare the osmolarities of two different solutions. There's another thing that's different from osmolarity called tonicity. Tonicity is how a solution affects the firmness or stretching of a cell when it's placed into a solution. Tonicity is also used to describe the effect that the solution will have on a cell. So if we draw a little aquarium here, and if we put our same cell inside of it, that's 300 milliosmoles, we'll have this in water. We can add two different types of solutions to it. There's going to be penetrating or non-penetrating. Penetrating or non-penetrating. One example of each, a penetrating solution could be 5% dextrose. Non-penetrating, 0.9% saline solution. What does this mean? Well, dextrose here is penetrating, so that means when we put it in solution, it's going to be able to diffuse in through the membrane of the cell and go into the cell. Saline, however, is going to try to get into the cell because there's less saline inside of it, but it's going to bounce off because it's not able to diffuse through the membrane. So depending on this is going to affect the tonicity. So let's say we put in, this is 300 milliosmoles. We put in a 0.9 saline solution. it's going to be 300 milliosmoles outside. So in terms of osmolarity, this is isoosmotic. And because there's no saline inside of this cell, it's going to try to get in, but it won't be able to. Because of that, the osmolarities are the same inside the cell and outside the cell, so the flow of water will stay the same. It's H2O. So, if the water does not flow in or out of the cell, what we would call this is an isotonic solution. We would say the cell is isotonic compared to the solution. Or the solution is isotonic compared to the cell. But if we draw another one here, what happens with dextrose, it's a penetrating molecule. So if we draw our cell again here, we're at 300 milliosmoles, which is actually the osmolarity of dextrose, of 5% dextrose. But once we put it in the solution, there's nothing inside this. There's no dextrose solution inside the cell. So all of it is going to want to go inside of this cell. And the funny thing about dextrose is that once it's inside that cell, the cell is immediately going to eat or digest or whatever. This dextrose is going to completely disappear. So it's going to keep going down its gradient because it keeps disappearing, so there's still a high demand for it inside the cell. And what happens is eventually there is no dextrose outside the cell. And we have a zero milliosmoles solution outside. And what happens is water wants to balance the osmolarity, so water is going to cross into the cell, and it's going to cause the cell to expand and get bigger. And what we would call this is a hypotonic solution. Because there's less osmolarity outside the cell, more osmolarity inside the cell, the water is going into the cell, it's hypotonic. But the interesting thing about this is the 5% dextrose compared to the cell was isoosmotic. So in certain cases, when the solute is penetrating to the cell, we can have an isoosmotic solution also be hypotonic. And that is about all that I'm going to explain on this. Thank you so much for listening, and have a great night.